Welcome to part 3 of my curve sketching series. In this video I'm going to show you how to sketch this curve by using a little bit of algebra and a ton of calculus. I'm not going to use a graphing calculator to graph it. I might use a calculator to get y values at certain x values, but I'm not going to use a graphing calculator to give me the actual picture. I recorded this video yesterday, and I posted it on my channel, but it actually turned out to be a little bit strange. The colors were all off. When I wrote a color down, it looked really strange. So I'm re-recording this, so this is going to seem like deja vu to me. But once I get this on there, I'll delete the other one. So this is ready to go. Here we go. We're going to start with a bit of a to-do list. Or if you watch my other two videos here, you're going to see that in part 1 and 2 we had these 10 things to do. Alright, and these 10 things, x-intercept, y-intercept, critical points, increasing, decreasing, inflection, concavity, and extrema. These first two are just algebra based. I have videos on those if you want to watch it individually. Critical points and increasing, decreasing, including minima and maxima, those are all first derivative videos. You can watch those separately as well if you're a little bit rusty on them. Inflection and concavity are second derivative items, and you can watch the separate videos on those too. So we're going to get started here, and at the end of this thing hopefully get a really nice sketch of this graph without having to rely on our graphing calculators. The first thing that I might do even before my to-do list is think about like what the graph kind of looks like. The end behavior of this graph is kind of important, right? We have a cubic polynomial, it's a 4-term polynomial, a lead term of 1, so it's a positive lead term, positive lead coefficient. It's an odd exponent. The end behavior is going to be up on the right and down on the left. So the general shape of the graph will look like that. So we need to keep that in mind as we sort of move along here. And maybe I'll write it, I'll draw that little sketch up here just to kind of keep reminded of that general shape. It's up on the right, down on the left. Alright, let's start with the y-intercept. This is definitely the easiest task. To find the y-intercept of a function, you just want to figure out where the graph crosses the y-axis. And to do that, at the point where the graph crosses the y-axis, the x value is 0. So you basically just replace all of the x's with zeros and solve. Everything turns to 0 except the -2. So my y-intercept is 0, -2. I'll put that right there. Yeah, maybe I'll just actually list it, 0, -2. So that's where my graph's going to cross the y-axis. So far I have just a general idea that it's going to look something like this. X cubed plus 2x squared minus x minus 2 is going to look something like that. Let's move on to x-intercepts. This is the other non-calc portion. We are going to want to set the function equal to 0. In other words, replace y with 0. This will tell us where the graph crosses the x-axis. In the past, you've probably heard these x-intercepts called zeros, or even just solutions to the polynomial. Alright, it's basically where the graph crosses this axis, and in this case it's going to be certainly at more than one point. So let's go ahead and figure it out. Right, the best way to figure it out is to try to factor it first. Alright, in this case it's not so easy to factor this. If it were a quadratic, like I showed you in example 1 of 3, it was a factorable quadratic. This one is certainly a cubic, so we have to be kind of creative, and that's where we're going to go back and remember our rational root theorem. The rational root theorem says that all the possible roots are going to be of this form, where c is this over here and a is the number in front. So we have all the factors of 1 and all the factors of -2. And that little formula there, C over A, is going to give us a list of possible solutions to this, possible roots. So let's think about what the factors of -2 are. This is our C value. And I think we can go 1 times -2 or -1 times +2. The factors of +1, this is our A term. 1 times 1 or -1 times -1. So the possible roots of this function are C over A. Alright, and what we're doing here is we're taking 1 from this column and 1 from this column. So we'll go green divided by pink, 1 over 1. Next, 1 from here, 1 from here, -2 over 1. 1 from here, 1 from here. I'm trying to get all the possible different sort of combinations. 1 from here, 1 from here. If I go down here and take -1 over +1, I've already got that taken care of. +2 over +1 is taken care of. +2 over -1 is taken care of. So what I want to do is list all my possible rational zeros, and I'm going to sort of simplify this, and I'm going to say, okay, I've got +1 and -1, positive, -1, -2 and +2, positive, -2. So those are not my x-intercepts, those are my possible x-intercepts. To figure out if they actually work, what I'm going to do is bring my function down here, give myself plenty of space. Now I need to do synthetic division. Alright, so let me kind of create a little barrier here. I'm going to do synthetic division. Oops. And by that I'm just basically just going to choose one of these. Let me put this right here for now. I'm just going to choose one of these 4 values. Let's start with +1. Just randomly picking a value. And I'm going to do synthetic division. Now if you're a little rusty with your synthetic division, go back and check it out, practice it. But basically what we're doing is we're taking all the lead coefficients of my polynomial. So 1, 2, -1, -2. And I'm just listing them just like that. Bring the 1 down, multiply 1 times 1 is 1, and add these two together. Multiply 1 times 3, add these two together. Multiply 1 times 2, and add these two together. When you get a remainder of 0, that means that x equals 1 is a solution or a root. That's an x-intercept. The factor of that then would be, if +1 is your root, then your factor is x minus 1. So when we take an x minus 1 out of our original function, if we divide that, which is what factoring is, oops, if we divide it out of there, we get x minus 1 and then this as sort of our quotient. And it's going to come from these coefficients here. Oops, it's going to come from these coefficients. But instead of x to the third, which is where we started, we're going to go x squared plus 3x plus 2. That's how that works. Once you divide, you just bring this down by 1. Let's see if we can factor this. I think it is factorable. X 2, 1 plus plus. And we still have the x minus 1 binomial in the front. So this is our sort of the new version of our function. We haven't changed its value, but we changed how it looks. And if we set this equal to 0, which is what we did up here, remember that's a whole goal here, is to figure out what x values will make this function 0. So we have 3 binomials all multiplying together to get 0, which means that either they're all 0, or one of them is 0, or 2 of them is 0. So let's solve them separately. And those are our x-intercepts. We haven't used any calculus yet. So up here on my graph, I'm going to put 3 dots at -1, -2, and +1. -1, -2, and +1. Those are my x-intercepts. So I'm finished with that. Okay, so now we are ready to go on to our study of a first derivative. So let me erase some of this stuff. I'm going to try to keep everything up in this top section here, because I always want to be able to look at my graph. Let me even get rid of these 2 things. So we've checked that off, we've checked that off. Alright, so we've got our function. This is our original function. What I want to do now is take the first derivative of it. The first derivative is going to give us y prime is going to give us the slope of our graph at any point. That's what derivatives do. They tell you the instantaneous sort of rate of change of a function at any point. To find the derivative, we're going to take the power rule. 3 times the thing in front is 3. Rewrite the x, bring the 3 down by 1. Same thing here. 2 times 2 is 4. Rewrite the x, bring your exponent down. 2 minus 1 is 1. I'm not going to write it there though. Negative x differentiates to just -1, and the -2 cancels out. So that's our derivative. Set that equal to 0. Alright, this thing is going to give us our critical points. That's what we're doing right now. We're trying to find out where our derivative f prime of x is equal to 0. Critical points are the locations of where your function has a derivative of 0 or the derivative doesn't exist. So we need to figure out what x values will make this whole left side equal to 0. And if you try to factor it, like you probably should at first, you'll see that it doesn't work. It's not factorable. So we've got to use our good old friend, the quadratic formula. So a is 3, b is 4, c is -1. This is algebra, so let's just go ahead and say, alright, the x equals -b plus or minus b squared minus 4ac all over 2a. And if you're watching this video, I'm assuming that you're pretty good at that, since that's like an Algebra 1 idea. So let's enter all the stuff in. -b plus or minus b squared, which is 16, minus 4 times a times c all over 2 times a. Simplify. -4 plus or minus 16 plus 12 over 6. Let's move this over here for a second and clear some of this space out. And let's keep simplifying. -4 plus or minus square root of 28 over 6. Well, you know that 28 can break down into 4 times 7. So we have -4 plus or minus the square root of 4 times the square root of 7 over 6. Again, I'm going to clear out this stuff. I don't need it anymore. The square root of 4 is just +2. So x is equal to -4 plus or minus +2 radical 7 over 6. And finally, we see that this term, and this term are all even. So I can cut them all in half. -2 plus or minus 1 radical 7 over 3. So there I go. I've got my 2 solutions. One of them is -2 plus radical 7 over 3, -2 minus radical 7 over 3. So these are what we call our critical points. That's where the derivative is equal to 0. Those are the x values that make your derivative 0. Remember, your derivative, I'll write it again, is 3x squared plus 4x minus 1. So these two values right here are where this derivative is equal to 0. So we can go up here and check off our critical points. I do probably want to get decimal values for those. So what I'm going to do is go to my calculator. Now, I told you I wasn't going to use a calculator to graph it, but this is where I'm going to use a calculator just to get a decimal idea. -2 plus square root of 7 divided by 3. 0.215. So this is 0.215. Let's do the other one. It's not a plus sign, but a minus sign. -1.55. I'll call it -1.5. Yeah, -1.55 is fine. So those are my two critical x points, x values. They each have a y value that goes along with them. When x is 0.215, let's figure out what y is. And to do that, I'm just going to use my calculator again. I don't feel like typing this whole crazy thing into my original function. I don't feel like doing that by hand, so I'm just going to use my calculator again, but I'm going to use it not to graph, but just to figure out a value. So I go to my y equals and I enter in my original function. It's got to be in my original function. And then when I enter that in, I go back to my home screen. I'm not going to graph it, but instead I'm going to go to variables, y variables. Let me do that again. Variables, press over to get y variables. Press enter. I want to pull up y sub 1 since that's where my function was entered in y sub 1. Once you have y sub 1 on your home screen, press parentheses and then put that value in, 0.215, and close parentheses. This will give you the y value when x is 0.215. And I get -2.11. Let's do the same thing for this value. Let's get the y value of our function when x is -1.55. .631. Alright, so those values are my critical points. Now what I want to do next to figure out what kind of points those are, right? Whether they're maxes or mins, or maybe they're something different. Right? The derivative can be 0 at points that aren't extrema. I need to test it, so I'm going to do my first derivative test. And that basically just looks like a number line. I'm going to put my two x values there, -1.55 and +215. I'm going to test it in my derivative down here and see what happens to my function up here. Derivatives give you the slope of a graph, so I'm looking to see if these values yield. I know that these values yield a 0 derivative, but I'm more interested in the values that are around it. So like what number in here, what number in here, and what number in here, what do those values do to our derivative? So we need to check that. What I'm going to do again is I'm going to rewrite my derivative right here. So I've got f prime of x is 3x squared plus 4x minus 1. I'm going to choose a number to the left of -1.55. Let's choose -2. Put that into your first derivative. So 3 times -2 squared plus 4 times -2 minus 1. So this is 3 times 4 minus 8 minus 1. 12 minus 8 minus 1. 4 minus 1 is positive. It's a positive number. Specifically, it's 3. 12 minus 8 is 4, minus 1 is 3. but positive means the graph goes uphill. Let's test a number that's in between these two. How about 0? Let's test 0 in our function, in our derivative rather. When we test 0 in our derivative, since 0 comes in between these two, I want to know what the derivative is, the derivative value. 0 here, I get that my derivative is -1. So it's a negative. That means the function goes downhill. Remember, derivatives tell you which way the function sort of goes, up or down. And lastly, we're going to want to pick a number over here. Let's pick 1. When x is 1, plug it into your derivative. 1 here, 1 here, 1 here. So that's 3 times 1 squared plus 4 minus 1. That's 7 minus 1 is 6. That's a positive number as well. So the function goes back up right there. It goes increasing as well. So that was our first derivative test. Now what that tells us is that anytime we see a function going from up to down, that of course is going to be a maximum. When it goes from down to up, that of course is going to be a minimum. Alright, so those 2 points right here, this is a minimum and this is a max. So I'm going to put those on my graph. I'm going to check it off on my checklist. I'm going to put them on my graph. 0.215 comma -2.11. Zoom in. So 0.215 and -2. So this is about 0.5. So 0.2 is in here somewhere. So I'm going to go right there and then down to about right here. Now I'm going to make my y-intercept a little bit smaller. And I'm going to make that maximum point a little bit bigger, or that minimum point rather. That's a minimum. I just graphed this right here. Let's also graph the max. -1.5 and then up 0.6. So left 1.5 and then up 0.6. So it looks like it's about right here. That's our max. Cool. Now in terms of increasing, decreasing, that's what we'll look at next. The function is going to increase every time that the derivative is positive. So the increasing interval is everything that's in red. -infinity to -1.55, and then we union 0.215 to infinity. That's where the function increases. The function decreases, it goes downhill everywhere that the derivative is negative. So it's in between those 2 critical points. So we've got that checked off as well. The only thing we have left then is our second derivative. We need to find our second derivative. So here we go. Let's go back to the right over here. We're going to work from our first derivative and we're going to find the derivative of the first derivative, which gives us the second derivative. So y double prime is equal to 6x plus 4. That's the second derivative. The second derivative tells us concavity. It tells us where the function is looking like that or looking like that. If it looks like this, it's a positive second derivative. This is a negative second derivative. This is a concave up. This is concave down. I also have a separate video on those if you're interested. So as we set our second derivative equal to 0, you'll notice we're doing the same thing that we did up here with the first derivative for inflection, or for increasing, decreasing, and critical points. We do the same thing here. We're kind of repeating that process. So when we set 6x plus 4 equal to 0, thankfully it's not too difficult. X is -2/3. I'm going to set that into a second derivative test. So -2/3 goes right here. I want to see the behavior of my second derivative and how it affects my original graph. So I'm going to pick a number to the left of negative 2/3, and I'm going to try it. I'm going to test it up into my second derivative. So a number to the left of negative 2/3, of course, is negative 1. So 6 times negative 1 plus 4 is negative 6 plus 4. That's a negative number. That means our concavity is down. Let's test a number over here to the right of negative 2/3. Let's test 0. If we put 0 in here, we get a positive. We get a positive 4. So our concavity is up. That's concave up, and this is concave down. The point where the concavity changes is called our inflection point. Concavity changes at the inflection point. So let's figure out the y value at that inflection point. We're going to go back to our calculators. Again, I'm not graphing with my calculator, I'm merely just finding y values. In the original function, I want to figure out what the y value is when x is negative 2/3. Negative 0.741. That's my inflection point. It takes care of that. The function in terms of intervals of concavity, it is concave up everywhere it's green up here, so from negative 2/3 to infinity, and it's concave down negative infinity to negative 2/3. So that takes care of these as well. Next thing we need to do is just graph. We're going to plot that inflection point. It's a negative 2/3, and so negative 2/3 is about right there. And we're going to go down about 3/4 of a unit. So it looks like right in here. The red one is the inflection point. Alright, so we've got everything finished. We did all 10 things. We're about a half hour into this video, and we're about to wrap it up and finally get to what we're supposed to be doing, which is to sketch the curve. I, at the beginning of the video, reminded myself that the graph has a general shape where it's up on the right and down on the left. Again, I got that from the fact that lead coefficient's positive and the degree is odd. So I need to just connect these dots the best I can, trying to follow this pattern, right? It's going to be up over here. That's not very good. It's going to be up over here and down over here. And I actually need to kind of fill in the blanks in between. So here we go. Let me zoom in a little bit so I can get a little bit closer look at it. So my minimum's down here, my inflection point, so it's going to go something like this, and then up. At the inflection point it changes and is concave down right there. So that's not too bad. Not too bad, right? The concavity changes right here. So to the right of that green bar, this is all concave up, that holds water, and to the left, all this sort of, the water will just fall off. So there you have it. Example 3 of 3. Hopefully it recorded better this time. And I'm actually probably going to end up doing a fourth example. I can end up doing like a dozen or 2 dozen examples, right? We can get into more complicated functions where they're rational functions and root functions and even trig functions and stuff. So over the next couple months I might put a couple more curve sketching videos on here, but I do plan on in the next week doing another one that is just purely a polynomial. So look forward to that. But there you go. There's example 3 of 3. I hope you enjoyed it. If you have any questions, just ask me in the comments section, and be sure to subscribe. Thanks for watching, and I'll see you in the next one.